When we talked about electronegativity, we talked about the unequal sharing of electrons in a bond between two atoms. And so that gives us the concept of polarity. And that is how hard each atom is pulling in an individual bond. We can look at polarity in individual bonds as well as overall polarity in the molecule dependent upon the shape. So the polarity depends on the difference in electronegativities between the two atoms involved. And that difference could even mean that there's an ionic bond if you have enough of a difference. If the difference between the two electronegativity values is above 1.7, you have a bond that has mostly ionic character. As you can see, it's a spectrum. There's lots of stuff that falls in between ionic and covalent, and that's what we call polar covalent. So here we have, between C and H, we have an electronegativity difference of 0.4. So that makes it, even though these are different atoms, the difference between them is so small that we would call that a nonpolar bond. But then you get in between here, OH and HCl. Those ones are clearly in the 0.4 to 1.7 range, being polar molecules. So let's do an example. Let's do carbon monoxide, CO. And if you look at the position on the periodic table, oxygen is far more electronegative than carbon. And so the electrons within these bonds are going to be physically closer to the oxygen. And we can draw a little arrow signifying that. And so we can also look at hydrogen, the H2 diatomic element, but these two have exactly the same electronegativity. So there is no what we call a dipole. The electrons are evenly spaced between these two hydrogens. If they're unevenly spaced, it's called a dipole. Sometimes, depending upon the shape, we can have an overall polarity or an overall non-polarity, even if we have polar bonds. If those polar bonds are symmetrical, then the dipoles can cancel out. Let's compare water, H2O, and CO2. So we've got water in its bent shape, and each of these bonds has a dipole going this way. These dipoles are headed roughly in the same direction. So we can say that this molecule has an overall dipole that goes that way. Now let's look at CO2. We've got C in the center and O's opposite each other. So these individual bonds have dipoles that go towards the oxygen, but they are pulling equally and in opposite directions. So the dipole cancels out. The two dipoles cancel each other out, and there is no overall dipole.